Okay, in this video I'm going to talk about the Legendre's formula for the p-adic valuation of a factorial. So basically, p-adic valuation is like it's denoted by nu p. So of n, by definition, it's the maximum power of p. P is a prime number, so like we suppose that p is prime. P is prime, and this is defined as the maximum let's say maximum k, such that p to the power k divides, let's write the other way, like n is divisible by p to the power k. So it's the maximum power of the prime number p, which is the divisor of n. So this is the p-adic valuation of a number, and the Legendre's formula, it says that the p-adic valuation of a factorial, so if we have the number n factorial, which is defined as the product of numbers from 1 to n, we can also write it this way as a product k from 1 to n. So the Legendre's formula says that the nu p of n factorial, so for any prime number p and any n, the p-adic valuation of n factorial is equal to the sum n over p to the power k the floor function, and the k varies from 1 to infinity. And okay, so let's write here that this is a definition, and this is the formula. This is the theorem. So it's important to notice that although we have an infinite sum here, like it's actually not infinite, like starting from a certain point, all the terms are simply zero. Like it's technically infinite, but like all the terms starting from a certain point are zero. This is because the denominator p to the power k, it grows with k. So when k is a large number, p to the power k becomes larger and larger, but the numerator is fixed. So when starting from a certain point, denominator becomes larger than the numerator, and therefore the floor function of such a fraction would be 0. So let's prove it. So the proof is actually quite simple. So we simply observe that so we have the n factorial, so this is equal to the product 1, 2, 3, and so on, n, right? The product of the first n numbers by definition. So when we count the kind of the power of p, so we fix a prime number p, right? Prime number p, and we count the power of p, which is a divisor of factorial. So we notice that somewhere, so let's say, so if p is greater than n, then there is nothing to prove here, like the factor, none of these numbers from 1 to n are divisible by p, and the p-adic valuation is simply 0, and the sum is 0. So like the formula is trivial. So p, the non-trivial case is when p is less or equal than n, right? So so somewhere here we have p. So this number p is divisible, like this number p contributes one power for which n factorial is divisible. Then the number 2p, if it is still less than n, then it also contributes, and so on. And so like let's draw it larger. So let's say n somewhere here, and we have all these intermediate numbers, right? So we have 2p, 3p, 4p, and so on. So all these numbers that are still less than n, each of them contributes one to the like to the p-adic valuation of n factorial, right? So then, so how many of them do we have less than n? So it's simply if we divide n by p, and we take the floor function, this would be the number of so this would be the number of numbers of the form kp that are less. So let's say the number of kp such that let's write the number of k's such that kp is less or equal than n. So the number of such items is exactly equal to the floor of n over p, right? So then when we take the apart from these numbers, there is also p squared somewhere here. So p squared, it contributes not 1 but 2 to this p-adic valuation, right? Because it's p by p, so p squared is like p by p, right? So it contributes 2p to the divisor to the divisors of n factorial. So and so does 2p squared, 3p squared, and so on. So because one of them is already counted in this, we need to add one more for each number divisible by p squared, if they are still less than n, right? So if these numbers still less than n, then we need to add one more divisor for one more power of p for each such number that is less than p, that is less than n. So, and how many such numbers do we have that are less than p? This is simply n over p squared, the floor function. So this is the number of such k that kp squared is the less or equal than n, right? And so on. So when we have p cubed, so if we have p cubed, if it is still less than n, then two of the divisors p are already counted in this set and in this set, and the third one we haven't yet counted. So the third one we need to count separately. And so similarly for 2p cubed, 3p cubed, and so on. So similarly we need to add one more for the multiples of p cubed. So we have that many of them. So this is the number of k such that kp cubed is less than n. So and we continue this indefinitely. We continue this indefinitely, and so eventually we get that new p of n factorial is exactly equal to the sum of these numbers. This, and so on. So it's exactly equal to n over p, the floor function, plus n over p squared, plus n over p cubed, plus and so on to infinity. And another way to write this is exactly the sum of n over p to the power k, k from 1 to infinity. This is exactly the formula that that we need to prove. This is the Legendre's formula. Yeah, so this concludes the proof.